Much of the content in this video comes from pages 15 through 25 of your textbook, and it's meant to help you achieve learning objective number 1, which is to distinguish between weather and climate, name the basic elements of weather and climate, and to list several important atmospheric hazards. In a moment, I'll ask you to pause the video and complete a very brief assignment. If you have not already done so, it would be a good idea to skim pages 15 through 25 before you start the video again. While you're skimming through the pages of your text, pay particular attention to the bold words, which should include the key terms listed here, and also to the figures in the book and their captions. Please plan to read the content more thoroughly before you attempt the online vocabulary quiz or the concept quiz for this chapter. As a quick but graded warm-up exercise, I would like you to write 2 brief statements about the place shown in this picture. The first statement should relate to the weather, and the second to the climate. Try to write at least a total of 2 complete sentences. Go ahead and pause the video and jot down your ideas now, or skim the reading and come back to this assignment. In this course, we will talk about both weather and climate, but it's important to note that these terms should not be used interchangeably. We consider weather to be a short-term condition, and that condition is constantly changing over time scales that range between hours to days. The term weather refers to the state of atmospheric conditions at a specific time and location. Some of these conditions, such as temperature, cloud cover, precipitation, and wind, are easily observable, and we're familiar with the rapid changes in those conditions. This is, for example, the Tacoma Narrows Bridge on the left-hand part of this slide. And you can see in this picture, it's subject to a buffeting by a big windstorm that's coming down the Narrows. The conditions such as temperature, cloud cover, precipitation, and wind are easily observable. Other conditions like humidity and air pressure at a specific location are much more subtle, and we have to make observations using scientific instruments to detect them. Climate, on the other hand, is a longer-term, more generalized view of the average weather conditions and of the variation in those conditions. Climate is based on observations that have been accumulated over many, many decades and includes information about extreme weather, such as record high temperatures and droughts. It's necessary, for example, for farmers to know the average rainfall during the growing season and the frequency of extremely wet and dry years. This is a very, on the right-hand portion of the slide, you can see if I assume these men are 6 feet tall, this is 18 feet in diameter. I see 2 huge saw blades measuring the diameter of this tree that they've just cut down. A very Western Washington picture here. What you can see in this picture are growth rings of these trees. And so trees are often used as a proxy for climate data. When there's good growing conditions, they grow a thick ring. When there are not such great conditions, they grow a much thinner ring. And if we count back from the day that this tree fell, we have a record that goes, in this case, hundreds and hundreds of years. A quick note before we go on from this slide. Down here at the bottom, I have quickly just kind of crammed in here the definition for the term meteorology. So we have weather being short-term changes, climate being long-term patterns, and meteorology is a third thing. It's the scientific study of the atmosphere. Although climatic data can be collected for a specific city, for example, look at the climate graph in this slide. It's for the city of Seattle. Climate information is normally used to describe larger regions. In this case, the monthly average precipitation values for Seattle are shown by the green bars. The blue, pink, and red lines that sort of crest in the middle of the graph show you the minimum, average, and maximum temperatures in that order. So you can see blue is the minimum, pink is the average, and red is the maximum temperature. If you're like me, this kind of chart drives you a little crazy because it's a lot of information on one chart. And in addition to the graphical information, they've put some numerical information on there too. But most of us in the United States have a hard time too. Those of you who are coming to us from just about any other country are in this regard a little bit have an advantage over us, because when we look at scientific weather and climate data, all of the air temperatures, for example, in this picture, are in degrees Celsius. So what I try to do is remember that a 25 degrees C day is about 77 Fahrenheit, a little bit warmer than room temperature. Also remember that water freezes on the road when it's 0 degrees Fahrenheit, 0 degrees C, or 32 degrees Fahrenheit. You can at least use this graph to determine that summers are warm in Seattle, and that they're dry, while the winters are cool and wet. I know that most of the participants in this class don't live in Seattle. They live closer to Edmonds, but it's reasonable to expect that precipitation and temperature values for Edmonds will be similar, if not the same, as those measured in Seattle. Both of those locations lie within just about the same climatic region. We would, however, expect the climate graph for Victoria, British Columbia, or Portland, Oregon, to start looking a little differently. In general, imagine what you think Spokane might look like in a climate graph. Is it wetter there or drier there? Is it cooler or warmer? Do the temperature and precipitation patterns follow the same seasonal trends? Once you've included that information for any city, that is the amount of precipitation on a monthly basis, the average temperature, and the seasonal effects, you've done a pretty good job of describing the climate. So in addition to Spokane, think a little bit too about Los Angeles, and I'd love it if you came to class next time ready to talk a little bit about these. What do you think about the maximum temperatures in Los Angeles when compared to Seattle? Relatively higher or relatively lower? The hottest days in July in this diagram are only about 23 degrees C. Does that make sense to you? That's this number right up here, the top of the red curve, where you see 23.4s for July and for August. What is that? It's about 74 degrees Fahrenheit. Similarly, the minimum temperatures make it look as though, let's see, where are the minimum temperatures? They are down here at, what is this, about 2 degrees C. So if we took this to be representative or as information about the weather, you might think that it never snows in Seattle. Is that true? What do you think explains the apparent disconnect between this climate graph and the reality of weather in Seattle? Is the climatologist that made this chart just incompetent? The answer is no. The reason the numbers don't seem to jibe with your personal experience is that the maximum and minimum temperatures are averages of each month's daily high temperatures and daily low temperatures. We'll work with these in an assignment coming up. Anyway, you can probably tell I get a little excited looking at climate graphs, but in a nutshell, weather is for short time scales with specific locations, while climate is an average data for long time scales and for larger areas. Okay, the next part of this first objective is to be able to name basic elements of weather and climate, and we're already well on our way to doing this. The nature of both weather and climate is expressed in terms of the same basic elements. These are quantities or properties that are measured regularly. And when we measure something regularly, we are monitoring. So carefully over some time scale, we're monitoring these changes. The most important elements that we'll discuss are shown here in pictures. I pilfered these from the internet, but you can see somebody here. This probably hasn't happened to you if you've never left Seattle. But when you get off into Minnesota, or if you've spent time in Wisconsin and North Dakota, the temperature of the air in the winter months literally freezes the moisture in your eyes, in your nose. And when you get down to that very, very low temperature, there is a real discomfort associated with it, to be mild. Also, this is a water bottle that was emptied at the top of a mountain and then driven to the bottom of the mountain. So at the bottom, the air pressure has caused this bottle to be crushed just under the weight of the molecules of air in the atmosphere. So it started as a full, uncrushed, empty bottle full of air up at, say, the top of Mount Rainier. When you bring it down to the bottom, down in Enumclaw, the bottle is actually crushed under the weight of the extra weight of the atmosphere. Humidity is something I grew up with. This is a poor guy out here. I imagine he's out mowing the lawn in Delaware someplace. That's where I grew up. The humidity of the air there also lends to human discomfort. So in the summer months, when the air is thick and moist, the heat effect is significantly greater. So discomfort is the standard daily factor that determines what you wear. In the summertime, it determines how much time you feel comfortable spending outdoors. So when you add the heat to the humidity and get the heat index, high heat index can really kind of keep you inside. Some other key weather elements, though: cloud cover and visibility. I'm not sure exactly what the specific links are to human health. You might think about seasonal effectiveness disorder. Some people just, boy, when the winter comes, it's gray, it's cloudy in this part of the world, and if you're used to sunny California or you're used to the Midwest, that has a bad impact on your daily outlook. So cloud cover, visibility is one of the things that we measure at weather stations. Precipitation went over here. Seeing some, a little bit um, of a misplacement of this tile in some of these pictures here. But you can see a standard downpour. This is looking out the window at a tree in the backyard. And right now I just see lines of precipitation falling down straight onto the ground. And so that is something we definitely would measure at a weather station. But also the wind. And here is the floating bridge over, I think that's the Narrows too. On the way down, you can see wind coming from this side because the waves are choppy here. And if you've driven across these bridges, you realize that these are scary places to be when the wind gets up to 30 and 40 miles an hour. These elements constitute the variables by which weather patterns and climate types are depicted. Although you'll study these elements separately at first, keep in mind that they're very much interrelated. A change in one of them often produces changes in the others. So if you followed along and you were doing a good job of this, I forgot that I added this question. What are some specific ways that these elements influence your life? The clothes you wear, how much, what you plant in your garden, what you plant in your farm, the cost of utilities, the health effects of cold and heat, etc. Natural hazards are a much bigger scale impact that weather can have on our lives. So every day, natural hazards are adversely affecting people worldwide and are responsible for a staggering amount of damages that I'll show you in the next slide. Some of the natural hazards are kind of off limits in a weather class because they pertain to the lithosphere, earthquakes, volcanic eruptions. Those are geologic natural hazards, but many, many others relate to the atmosphere. For most people, occurrences of severe weather are far more fascinating than ordinary weather phenomena. A spectacular lightning display generated by a severe thunderstorm fills you with both awe and, in a lot of cases, fear. Of course, hurricanes and tornadoes attract a great deal of much deserved attention. A single tornado outbreak or hurricane can cause billions of dollars in property damage, a whole lot of human suffering, and death. The chapter that we're working in here gives you on pages 21 through 25 a quick description of some of the ways that weather can influence your life. I can see here, for example, the winter storms shown in the top left picture here. The extra weight of ice falling on telephone lines or power lines can, do away with your ability to turn on the light or heat water or heat your house. These hazards happen in places you wouldn't think. My sister in North Carolina deals with these winter storms on a routine basis. Power goes out and it'll stay out for days until they can get it fixed. You see in the top middle picture, a man shoveling out after Hurricane Sandy. That was 2013. You guys probably all remember that. Big news coverage of the storm. So that's not snow he's shoveling, it's sand. It's not going to melt and go away. He's got significant damage to his car just by having that much sand around it. And he's going to see if his car doesn't work now after getting, looks like about 2.5 or 3 feet of sand deposited by a hurricane in his neighborhood. The bottom left shows you an instantaneous hazard that comes with thunderstorms, lightning. A huge, scary part of storm chaser videos, for example, are when the people get a little bit too close to the tornado, a little bit too close to the thunderstorm, and you can see static electricity. Maybe you've seen this too, even climbing on some of the mountains around here in Washington. You are out in a clearing at a high altitude, and all of a sudden your hiking partner's hair starts to stand up on their head. Well, those are runners that are going up towards the sky and could draw down lightning. So when you see that happen, get low, don't lie down, but crawl into an area with a little bit more cover. That is not to say go run under the nearest tree. We'll talk more about hazards of lightning later on in the course. But this tornado, which was photographed in Joplin, Missouri, did the damage shown in the bottom middle picture here. So when we say billions of dollars of damage, it's not just this neighborhood, but the damage for this tornado goes in a linear way all across the region. Finally, the picture over here on the right shows you the long-term effects of another hurricane. But this wasn't hurricane damage. This flood is the river cresting because of a huge amount of rain dropped from the sky by the hurricane. So yeah, it did come after the hurricane, but it's an indirect hazard associated with the hurricane. So this question here, what are the specific ways that hazards can influence your life? We all have a good idea of, what might happen if we were around the base of a tornado, and we'll go into depth about tornado hazards later. But if we, just kind of glancing through these pictures to get an idea, we're talking about power outages from ice storms. We're talking about the loss of mobility for this guy and for the guy in the bottom picture. I can see a bunch of overturned cars. Loss of life, almost definitely some loss of life in the lower center picture. Loss of property. So I can see some human effects in each of these pictures. Of course, other atmospheric hazards adversely affect us. Some are storm related, like blizzards, hail, freezing rain. Others are not direct results of storms. Heat waves, cold waves, fog, wildfire, drought, all of those are important examples of non-storm related atmospheric hazards. In some years, the loss of human life due to excessive heat or bitter cold exceeds that caused by all weather events combined. Moreover, although severe storms and floods generate more attention, droughts can be just as devastating and carry an even bigger price tag. The figure on the right here shows that between 2000 and 2013, the United States experienced 84 weather-related disasters in which overall damages and costs reached or exceeded $1 billion. The line graph shows the number of events that occurred each year, and the bar graph shows damage amounts in billions of dollars. So the total losses for 84 events combined exceed $600 billion. So this is a graph that I know we see a lot of in textbooks and in teaching slides and things like that. This presentation, I'm guilty of putting it up here. One of the things you have to be really cautious about is whenever you see a graph that combines these sorts of axes, right? Because if this is the total number of events and this number 15 was squished down to be an appropriate unit down here. So this 15 matches this 15. Well, that tends to make this graph look not so impressive, right? So one of the things that the author is doing with this graph, and this comes from NOAA, the National Oceanic and Atmospheric Association, this is meant to cause a response in your mind, right? Here's 2005, and I see a huge number of billions of dollars, $190 billion. This is Hurricane Katrina, okay? And that is a storm that hit one critical location. It wasn't necessarily a big weather event year, right? There were only 5 big events, but it sure was a big price tag just because the storm happened where it did. 2011, this is a different story. Many weather events, but an average amount of damage. Well, better than average, but not nearly as much as there was in 2005 or 2012 because of Hurricane Sandy. So we have to be careful about these. And there's another one, let's see, figure, I think it's 1.34 in your textbook, has a very similar picture on it. And it's okay with me if you're a little bit skeptical as you read those. So to summarize, what you should be able to do at this point is define and distinguish among meteorology, weather, and climate. Right? We've already done that. Meteorology, the scientific study of the atmosphere, weather, the state of the atmosphere at a given time and place, and climate is the sum of all the weather information statistically for a place or a region. The second part of objective 1 is list the basic elements of weather and climate. So I have all of the weather elements, all of the major ones listed here. And the important climate ones are in bold. So air temperature, humidity, cloudiness, precipitation, air pressure, wind speed, and direction. Each of those is a weather element. And most of the time, when you're talking about physical climate, we're considering mostly air temperature and precipitation. 3, can you list at least 5 storm-related atmospheric hazards? So I ask you, we've got 3 here in this table that I showed you on the last slide. I'd just like for you to think of 2 more and bring that to class with you. So think of at least 5 storm-related atmospheric hazards. For example, lightning, blizzards, and hail. And 3 atmospheric hazards that are not directly storm-related. And you can use these to satisfy that. They're fog, heat waves, and drought. Those things happen independently of storm activity. And so finally, for this video, I'd like to go back to the picture in the first slide and ask you, now that you've had a little bit more in-depth information about weather versus climate, will you review the statements you wrote down at the beginning of this lecture? And if you changed your mind about them, write a more correct version without erasing the first statements. So you're not going to be graded harshly one way or the other. But you're certainly not going to be graded on what you knew going into this presentation. I'm just interested in seeing if any of this information changed your mind. So bring these statements in and turn them in during our next class session. Thanks for watching.